let's discuss contact forces. In this video, we are basically going to talk about the normal reaction force and about friction. You probably know that there are two types of friction, the static and the kinetic friction. So we are going to see how these things are different and so on. So first of all, let's talk about what normal reaction force is. So suppose you have your favorite physics textbook on your table. Of course, if you just leave it on the table, it does not, it doesn't have any vertical velocity, right? It doesn't move up or down. It's, sticks to the table. So let's think of what the forces acting on this book are. We have two, right? We have the force of gravity, mg, on the book, and because the book is not moving vertically up or down, that means that this vertical force must be balanced. There should be no net vertical force on the object. And we know that there is another force called the normal reaction force. This is a force provided by the table on the book, right? And we denote it as N. Because the book is not moving up or down, we then say that in this situation, N is equal to mg. By the way, because N is equal to mg and they act in opposite directions, there is a very common misconception that N and mg constitute a third law pair, and this is absolutely not true. So N and mg are not third law pairs. That should be obvious because notice that N and mg act on the same object, which is the book. We know that for a third law pair, right, the forces should act on two different bodies. So in this situation, there are third law pairs. Let's look explicitly at what they are. The third law pairs in this situation are, number one, if you look at the force mg, which is the force exerted by Earth on the book, the third law pair to that force is actually the force on Earth by the book. So like the Earth is pulling the book towards it, and equivalently the book is also pulling the Earth towards it. And the other third law pair is, because we have this N, which is the force on the book by the table, the third law pair to that is that the book also exerts a force on the table, right? So the third law pair is the force on the table by the book. So again, notice that these two forces are on two different objects. One is on the book and one is on the table. Basically, the normal reaction force is responsible for keeping the book on the table, right? If the normal reaction force were not there, the book would just fall down. A table is like preventing the book from falling down, and it's preventing it by providing this normal reaction force. So now that we know what a normal reaction force is, let's look at friction. Let's start by thinking about kinetic friction. So suppose that you push your book with some kind of force. You push it in such a way that it slides with a constant velocity v along the table. Now, apart from this force F with which you're pushing the book, there are other forces acting on it. One, as we know, there's the mg and the n, but mg and the n are balanced with each other, as we mentioned. After all, the book's just sliding in the horizontal direction. So what does Newton's second law tell us? Newton's second law tells us that if the resultant force on a body is zero, then and only then will the body maintain a constant velocity. So in this real world situation, right, where you're pushing the book and causing it to move in a constant velocity, it must be that your push is being balanced by some other force, so that the resultant force on this book is zero, and that's why this book is moving at a constant velocity. And we happen to know what that force is. This is one of the most important forces in the real world. It's called friction, and let's call this F, kinetic friction. Why is it kinetic friction? Because since the body is moving, the frictional force can be classified as kinetic friction. We will see that there's another type of friction very soon. Now, what are the properties of kinetic friction? The properties of kinetic friction are, number one, it depends on the interface. For example, if instead of pushing your book on the table, you were pushing it on on a piece of sandpaper, you would have a much larger force with which you would have to push the object and still have it move at constant velocity. So it depends on the interface between the book and the table, right? So it depends on whatever this interface is. And the second thing is that it can be, and this is a empirical or an experimental fact, that the kinetic friction is actually proportional to the normal reaction force, and that's given by this: the magnitude of kinetic friction is equal to mu k times n. So the kinetic friction is proportional to normal reaction force, and this mu k is a property of this interface, like we said. So if mu k is large, then for some given normal reaction force, the kinetic friction will be large, so that this mu k obviously is a property of the interface. There are some more interesting properties of kinetic friction, but for now these two are the most important ones that we have to deal with. Specifically, when doing problems, you will often be given the coefficient of friction, this mu k, and you might be asked to do some calculations. Now let's talk about static friction. So suppose that initially your book is stationary on your table, and then you start applying a small force on it. Experience tells us that with this small force, the book does not move forward. If you increase the force by a little bit more, perhaps again the book fails to move forward, and you kind of keep increasing the force and increasing the force, and suddenly after you've increased the force by some critical value, right? So after the force vector has become a certain length, perhaps, suddenly what you find is that the book starts to accelerate. So what's going on here? So clearly there's for each of these situations, when for example you had a small force F that you were applying, clearly there must have been a force of equal magnitude that was pointing backwards. When you increase the force by just a little bit more, right, there must have been a force that's equal to this but acting in the opposite direction on this book, right? And then you kept increasing this force F and increasing this force F, and the book wasn't moving, and after a critical value, what happened is that the book suddenly starts to accelerate. So this force that's being developed, that keeps increasing and acts in the opposite direction, clearly that has a limit to which it can increase, right? And after that limit, suddenly this force vanishes and is replaced by perhaps a slightly smaller force, and that's why after you reach that critical magnitude for this forward force vector, the book doesn't stay stationary or move in constant velocity, but suddenly starts to accelerate. How can we capture this mathematically? We say that this force being developed and slowly being increased as this F keeps increasing, this force is the force of static friction. Let's call this F static friction. And so clearly this static friction does not have a constant value or like the kinetic friction did, but rather this could increase and this could increase to some maximum value. We can capture this again. Frankly, this is an experimental observation that F static friction is less than or equal to some mu s times the normal reaction force. So this static friction can have some value between 0 and the maximum value it can have is mu Sn. Mu S is obviously called the coefficient of static friction, and the maximum value of static friction is proportional to actually the normal reaction force. Now when a body starts to slide, the frictional force graduates to the kinetic friction, and it turns out that the kinetic friction, which is given by mu Kn, right, turns out to be less than mu Sn. In other words, it turns out that typically mu S is greater than mu K, which means that the maximum value of static friction is typically more than the maximum value of static friction is more than the constant value of kinetic friction. It's often actually interesting to see which direction the static friction acts. You will see that in some problems it's not intuitive or obvious at all. But with that, let's end this discussion on contact forces.